Well, hello everyone. This is Chris back again with the Ancient Scholar. Hope you guys are doing well. Today I'm just going to continue talking about pH, and basically what I'm going to do is I'm going to backtrack a little bit, and I'm not going to actually really talk much about that scale, the 0 to 14 scale. What I'm going to start talking about is actually answering a question, which I think is a good question, and that question is how do we really measure hydronium ion concentration? Remember, hydronium ions being hydrogen ion, being a proton, all having essentially synonymous meanings. So how do we really measure hydronium ion concentration? How do we really measure acid? Because clearly when we're talking about individual atoms, to measure individual atoms, we're going to be talking about very, very incredibly large numbers. And what is that special number that allows us to transition from the microscopic world into the macroscopic world? And that's a number that we're exposed to very early on in our core chemistry courses, and that is something known as a mole. A mole. And what is a mole? Well, a mole is an incredibly large number, and it's actually 6.02 times 10 to the 24 atoms. So that many atoms. And just to review, this was something called scientific notation, and basically what that is the way of making a really big number or a really small number much more manageable. So actually what that is 6.02, and then my decimal point moves over 24 times. I'm not actually going to, but whatever that number, 6 quintillion, whatever number that is, so it's that many atoms equals 1 mole. And we know from chemistry that if I were to look at, say, hydrogen on the periodic table of elements, I'd have the atomic number of 1, that's the number of protons, and I'd have this 1.001, the atomic weight. And what this 1.001 means is if I have 1 mole, 6.02 times 10 to the 24 atoms, individual atoms of hydrogen, it would be about that much grams. So 1 mole of hydrogen is going to be about 1 gram, a little more, give or take a little bit, depending on the different isotopes. But we can generally say, for government work, that we've got about 1 gram of hydrogen in a mole, and that really is the basis of measuring acid, is the mole. So I'm just going to go ahead and erase this. And if you can see, I have a little container here, and if you can imagine that I have 1 liter of fluid, we'll say water at a neutral pH, even though we don't quite know what pH is yet, or maybe some of us do and some of us don't, but we have a container of 1 liter of liquid. So if I were to put 1 mole, of hydrogen, and now let's change it a little bit. Let's not make it hydrogen, let's make it hydrogen ions. 1 mole of hydrogen ions, and I dump them into that container, and of course they'll rather quickly become hydronium ions. But if I were to put 1 mole of hydrogen ions in there, I'd have a concentration of 1 mole per liter. Hopefully everybody sees that. I'd have 6.02 times 10 to the 24 individual atoms, or individual hydronium ions floating around in there, give or take. And that is how we measure acid. Don't worry about the pH scale. We're going to get to how that scale comes about. But that's how we measure, is the number of moles of acid, of hydronium, of hydrogen ions I have per liter. Now clearly 1 mole per liter is pretty concentrated. I hope everyone would agree. You know, that's quite a bit. So under normal circumstances, certainly under biological circumstances, we're not going to be dealing with 1 mole per liter. We're going to be dealing with parts of a mole, right? Because a mole is just a number, right? So I can have fractions of a mole. Fractions of a mole. Okay? And that's really what we're going to really be dealing in the biological, from a biological standpoint, from, say, the human body, where, you know, my pH is 7.35 to 7.45, just a little on the basic side. We're not going to be dealing with a mole per liter. We're going to be dealing with a fraction of a mole per liter. And that's where things kind of get rather complicated. That once I start breaking this mole down into fractions, these numbers can get exceptionally small. So let's say that I start off with 1 mole per liter. Okay? And then I want to make this, so let's just say that that's as concentrated as I'm going to get under any realistic circumstance. 1 mole per liter. Let's say that I want to then weaken that a little bit. I want to dilute that. How can I? Well, obviously I'm going to add you know, some more fluid to that to dilute it out. But let's say that I want to make this 10 times less concentrated. So 10 times less concentrated. So that would give me how many moles per liter? Well, if 1 mole per liter is 100% concentration, we'll just say 1 mole per liter is our base. Then what is 10 times weaker, or 1/10 of a mole? Well, that's just nothing but 0.1 mole per liter. And let's say that I want to make, so this is 10 times weaker now. Let's say I want to make it yet another 10 times weaker. Well, that would be 0.01 moles per liter. And let's say I want to make it even 10 times weaker or less concentrated. Well, that's going to be 0.001 moles per liter. And let's make it 10 times weaker yet, 0.0001 moles per liter. Okay. Now clearly, as I make this weaker and weaker and weaker, as I have less and less acid in here, my concentration decreases, I'm going to have a whole lot of zeros. And when we talk about documenting and charting in regular situations, these numbers are going to be very difficult to work with. First of all, because it's easy to make a mistake. And second of all, just because, I mean, charting is going to be just massive. All these points and this and that. And is there some way of taking this concept that I just talked about? Is there some way of taking this concept and putting it into numbers that make common sense? So, whole numbers. Is there a way of taking this mess and kind of putting it into whole numbers? And that will be the topic of subsequent videos. So hopefully you guys are starting to get a little intuition, at least on how we measure acid concentration. And then we'll talk about how we actually turn this concentration and all these zeros into those whole numbers that are a little easier to work with. Okay guys, take care.